one solve what?
So this is the problem of a simple bar having fixed the area. It is a constant area throughout the length. See, for example, the area of this is given as 300 millimeters square. This is having uniform cross section throughout the length, and it has got its own Young's modulus is also fixed, which is given by 200 gigapascal, and we can definitely take it as 200 into 10 raised to 3 megapascal. This is the speciality of this particular problem is, in the last problem we have seen both the ends are fixed. Both ends, this end and that end was fixed, and obviously we had divided into 4 nodes with 3 elements. So obviously we had fixed the node 1 and node 4, so therefore the total thing was 0. But in this condition, this particular problem, you can see that the left hand side is totally fixed, whereas on the right hand side there is a small gap. The structure can deform within this gap. After that, it is going to be prevented. So therefore, the stresses will start inducing in this member only after it has deformed by about 0.12 mm, and after that, whatever is being prevented, that will induce the different kinds of stresses in these members, either it may be tensile or compressive, depending on this. Now, next speciality of this problem is, though the bar is of 300 mm length, but since the load has been shown at the midpoint here of 600 kilonewton, obviously we need to discretize the given element at that particular point. So therefore, this same problem will be now handled as a 2-element problem. This is going to be element number 1 and this is going to be element number 2. So therefore, if I want to represent this in the problematic form, this is going to be of 2 elements with 3 nodes, 1, 2, 3. So obviously, these are my displacements, Q1, Q2 and Q3. These are the displacements, and of course the forces are going to be F1, F2 and F3. You consider them as the respective forces which are acting at these three nodes. What we find out is here is the boundary condition has been specified at node 1 and at node 3. These are the two boundary conditions which have been specified. So therefore, I equate Q1 to A1 and Q3, I will equate it to A3. But you can see from the figure that A1 is obviously fixed because it is fixed, Q1 is 0 and obviously A1 is also 0. Whereas in the third case, this is the third node, definitely A3 is not 0 because this is not fixed. There is a small gap of 0.12 mm, that is called specified displacement is there. So we need to take A3 equal to 0.12 mm. So then before we have to follow the same conventional method, discretize, write down the element stiffness matrix for both element number 1 and 2 and then find out the global stiffness matrix, element vector and the force vector. Let us write all the three first and then we will go for the treatment of boundary conditions and all that. First, let us write element number 1. I want to write the stiffness matrix K1, which is given by the AE upon L, A being 300, this is 200 into 10 raised to 3 upon 150 into bracket 1 minus 1 minus 1, 1. This will give me the, comes out to be 10 raised to 5, 4, minus 4, minus 4 and 4. See, if you look at the element connectivity, the node numbers are 1 and 2 for the first element. So therefore, this is to be written for the first element. And looking into the similarity, because if you look at the second element, all these parameters are going to remain same. So obviously that means that even the second stiffness matrix is also going to be the same thing. Like this is going to one and the same, but your element connectivity will be different here. Now it will be 2, 3 and 2, 3. This is how we have to find out the element connectivity. Once we write the element stiffness matrix for both element number 1 and element number 2, we need to first find out now the global stiffness matrix. So let me write global stiffness matrix, and this is going to be capital K. And you know, since there are 3 degrees of freedom, so it is going to be of 3 by 3 size. This is of 3 by 3 size, which is given by 4, minus 4, 0, minus 4. Here 4 plus 4 is getting added. Here it is 0, here it is minus 4, and this is minus 4. So these are going to be what are called as the global stiffness matrix. We will get this. And as far as the force vector, or of course Q is concerned, if I write it in the row form, it will be Q1, Q2, Q3 with the transpose, because I need to write in the column form. So this is going to be there. And similarly, if I want to write the F, it is going to be again F1, F2, F3, transpose Newton. So this is going to be the global stiffness matrix vector, then nodal displacement vector global, and the global force vector. We are going to write that. And once we write the FEM equation, the KQ is equal to F. We need to write that. See, because of this, the force vector is supposed to be modified. How we are going to modify, you tell me? See, for example, this is going to be there. Here it is F1, F2 and F3. And if you want to show the effect of these boundary conditions which are shown there, we need to again go over this. For example, if I write this in this particular form, this will be K11, K21, K31, K12, K13, K22, K23, K32, K33. Okay, this is the way this particular elements are being represented. Now, how exactly this is going to be reflected? And as you are already aware, by using the elimination approach, since the boundary condition is specified at node 1 and node 3, obviously I have told you that the first row and first columns are getting eliminated, third row and third columns are getting eliminated. So this eliminated, whatever it is there in the first row, that is going to be reflected here. For example, this will be written as K11A1. This is K21A1 minus K31A1. This will take care of the modification in the global load vector when we consider the first boundary condition A1. In the similar way, when we want to consider the second boundary condition at node 3, we need to consider all these which have been eliminated. That is K13, K23, K33. So here again, I am writing it as K13, A3, K23, A3 minus K33, A3. This is what you have to write as far as the modified, you can say, global stiffness matrix is concerned. So therefore, let me write this equation again. Once again, write like this. This is going to be 4 minus 4 0 minus 4 8 minus 4 0 minus 4 4 here, and here I will be taking Q1, Q2 and Q3. Now I would like to again call upon here, since your value of A1 is being 0, all these are not necessary to be written. This all will not be necessary because A1 is being 0, directly I can eliminate them. So what I will write down in this modified version is F1 minus K13A3, F2 minus K23A3 and F3 minus K33A3. This is the modified, you can say, load vector I am going to write before I apply the elimination approach. Now, during the elimination approach, I have already told you, since Q1 is equal to A1 equal to 0 and A3 is given as 0.12 mm, I need to eliminate node 1 and node 3. That is this will be removed. The entire row and of this 1 and 3 are being eliminated. First row, first column are eliminated as far as node 1 is concerned. Third row and third column is getting eliminated because of that. So what is left here is now 10 raised to 5, 8 into 10 raised to 5, Q2 is equal to F2 minus K23A3. Now F2 is the load applied, it is 600 into 10 raised to 3, that is there, minus K23. K23 is what here? Minus 4 into 10 raised to 5. Please remember, this particular K23 represents this along with this 10 raised to 5. And since it is having a minus sign, I will write 10 raised to 5 into A3 being 0.12. So this is going to take care of the right hand side of the load vector. So now solve for Q2 and you will be getting the displacement Q2 as 0.81 millimeter. This is what you will get. So therefore, if you want to write the global, you can say, nodal displacement vector, it is 0, it is 0.81. Please remember, last one is not 0, it is going to be 0.12 mm, which has been already specified. So now we will come to all these three displacements as far as this is concerned. So once we know the displacement vector, now I can calculate the stresses and supports, reactions and all that can be easily calculated with the help of this. Now I will show you how to calculate the stresses in both the elements. See, logically, if you look at this particular figure, you can definitely see when I take the first member, this particular first member, if you take only the first member, because of this load, this definitely it gets elongated. Therefore, it is under tension. This member, the type of the stress induced in the first member, because it is getting stretched, it is tensile in nature. Whereas in the second member, the same force is trying to push this, and once it touches this, the remaining is all prevented. Even though it would have deformed if the wall would have been not there, the member would have been deformed to that extent. But since because of the presence of the wall, the deformation is, you can say, prevented, and this will induce a compressive stress in that. So that definitely we will see the results, and we should get the similar type of results. I should get that. So therefore, now I will write stresses. first element number 1 I will take. And yesterday in the last lecture I have already told you this is written in this form with a Q1 and Q2. For this we have to write this, and for this definitely it is Q1 and Q2. As far as the element number 1 is concerned, it is Q1 and Q2. So therefore, if I want to write the same thing, it is 200 into 10 raised to 3 divided by the length of the first element. It is minus 1 and 1. And here, if you look at this, 0 and 0.81 are the Q1 and Q2 of this. Here, what is this is? This is Q1, this is Q2, and this is Q3. So therefore, when I calculate this, I should get a tensile stress of 1080 megapascal. Here, this plus sign indicates that the stress is tensile in nature. This is what is going to be shown here. To find out the stress in the second member, okay, what we have to do? Sigma 2, and Young's modulus being the same, there is no need of taking all this and 1, 1. Here, again you will write Q1 and Q2 only, but in this case, this is Q2, this is going to be Q3. For this particular second element, you can see there, looking at the connectivity, it is going to be, of course, you can always form this table, local node number 1 and 2, and element number 1 and 2. See, global node number for the first element is 1 and 2, for the second element it is 2 and 3. So these are going to appear even at element stiffness matrix. The same number will appear on the respective element stiffness matrix, and the same nodal displacements will be considered when you are calculating the stresses. So since the material is being same, 200 into 10 raised to 3 will be there, this is 150 will be there, minus 1, 1 will be there, and here it is 0.81 as well as 0.12 need to be taken here. When you calculate this, as expected, I will get a negative sign. That means I will get a compressive stress. I will get a compressive stress. See, this will automatically tell you the type of the stress which are induced and their magnitude. Now coming to the last part of this particular analysis, that is support reactions. Support reactions, you have many ways to do it. Let us say I will do this like this. Suppose if I take general equation, I told you R is given by K, Q minus F. So if you take in the similar fashion, this R is nothing but here because there are 3 nodes, R1, R2 and R3. And as far as this is concerned, you are already knowing it is 4, minus 4, 0, minus 4, 8, minus 4, 0, minus 4 and 4. This is going to be the global stiffness matrix, and the nodal displacements already you know it. First one is 0, 0.81, 0.12. This already you know. Minus 0, 600 into 10 raised to 3 and 0. Because there are no loads given at node 1 and node 3. That is why F1 and F3 are 0. And if you solve for this, what you will get is reaction R1. After solving, you will get 324 into 10 raised to 3 Newton, or minus 324 kilonewton you will get. And R2, obviously, since there is no support at node 2, it has to come 0. And R3, again it is going to come minus 276 into 10 raised to 3 Newton, or minus 276 kilonewton. And I have already told you, if you add this R1 plus R3, it should be always equal to P. That is, of course, this is going to be with the negative sign, and this should be equal to that. That means if I add these two reactions, I should get the total load of 600 kilonewton. So that will, you can say, cross-check that your displacements and all other things, whatever you have found out, they are correct or not. If this is not telling, that means something is wrong in your solution. So to go back and check for the nodal displacements again, and if they are coming correct, then finally we'll reach this particular final equation. We'll reach that. I hope you understood the problem. So it is a very, very simple problem. Now, very much similar to this only, I will consider one more problem where I will solve this with the help of both elimination approach as well as penalty approach, so that you will compare both the answers will be almost identical, and how to solve the same problem by both the methods. I will show you that. Okay. Next, let us take another problem. It is very much similar to the one what we have just now done, but the load is different. Everything is same, almost everything is same, but area and the loads are going to be different here. This is again as usual 150 mm only. This is also 150 mm, and the load here it is 60 kilonewton, not 600. Okay, and area is given 250, or I can write it here. Area of the bar A is 250 millimeter square, and Young's modulus is again a steel, that is GPa. Almost everything will remain same, and we need to calculate the displacements, stresses, as well as the reactions by both the methods. Okay, let us start with the up to global stiffness matrix. The procedure remains same. Once you get the global equation, FEM equation, KQ equal to F, whatever modification in that need to be done depending upon the type of the boundary handling condition method, either whether it is elimination approach or you can say penalty approach. So let us first build that. So let me consider first the element stiffness matrix for the, you can say A1 E1 upon L1 into bracket 1 minus 1 minus 1 1. This I want to first find out. Area being 250, this being 200 into 10 raised to 3 Newton per millimeter square, and this is being 150. This is 1 minus 1 minus 1 1. Okay, this will directly give me what you can say 10 raised to 5 into bracket 3.33. This is also minus 3.33 and 3.33. This is for the first element, and obviously this is again 1 and 2, 1 and 2. So no need of telling that again in the similar way you need to always form a element number 1 and element number 2, because of the problem here always you have to divide this. This is a must. So therefore there are 3 nodes with 3 displacements and all that. In the similar way, because as I told you, all parameters being remaining same, we just get the same matrix here. This will be same only, but only the element connectivity will change. It will become 2 3 and 2 3. This is what you are going to get that, and from this you can find out what is called as the global stiffness matrix, capital K, which is going to be what, 10 raised to 5 into bracket. This will remain 3.33 minus 3.33, 0 minus 3.33, 6.66 minus 3.33, 0 minus 3.33, this is 3.33. This is what you will get, and these are 1 2 3, 1 2 3. This is what you are going to get that, and as I told you, after this the real method of will start now. That is how to start the load. Say for example global load vector. Tell me how exactly it has to be done. It has to be done in the similar manner, F1, F2, F3. And if you are using, first let us solve it by elimination approach. In the elimination approach I told you the last row, this need to be calculated. That is K13 A3 minus K23 A3 minus K33 A3. This is going to be the modified equation for F. Of course, there will be first row is also there, but we are not taking, because why we are not taking? A1 being 0, this will automatically go out. This particular things A1, because in this particular problem also A1 is fixed, that is 0, and A3 being 0.12 mm, that is small gap. Okay, so therefore I am not considering this equation, only I am considering this equation. So now if I want to write the KQ is equal to F, let us write the global FEM equation first, and then we will see how exactly it is going to be operated. That, see, 10 raised to 5 into bracket 3.33 minus 3.33, 0 minus 3.33, 6.66 minus 3.33, 0 minus 3.33, and 3.33, and here I will get Q1, Q2, Q3, and the last one is, since there is no load, F1, and here you have the, say F2 is 16 to 10 raised to 3, and here there is no load here, and apart from this, minus, what is that? K11, yeah, last K13, it is again 0 into 0.12. For this, it is minus of minus 3.33 into 10 raised to 5 into 0.12. This need to be taken for this, and for this, of course, it is 3.33 into 10 raised to 5 into 0.12. This need to be taken in the beginning. You have to write that. Depending upon which type of method, this is purely for elimination approach. So according to the elimination approach, since node 1 is fixed, I need to eliminate first row and first column. Similarly, the third node, the boundary condition is specified. So wherever it is specified, I need to eliminate this row and this column. So what is left is this much, Q2 equal to all this. So therefore, let us write this equation, 6.66 into 10 raised to 5, please don't forget this, 10 raised to 5 is equal to 60 into 10 raised to 3 minus of minus 3.33 into 10 raised to 5 into 0.12. This is going to be the total equation, what you are going to get that. So by solving this, what I will get is Q2 will comes out to be 0.15009. You will get that. So therefore, your global nodal displacement will be 0.15009 and 0.12 transpose m. So this will give you the complete nodal displacement vector. So with this, you can definitely find out the stresses and all these things. I don't want to show you that. Directly I want to find out the reactions. Stresses are simple. Again, in the same way, you can use sigma 1 is equal to E1 by L1 minus 1, 1. And for this, you can take Q1 and Q2. You can find out that. And sigma 2, I have not calculated for this. You can do it. Definitely, you can do it as a practice. In the just same way, you can do this and get the, see, as I told you, you will get a tensile stress, here you will get a compressive stress. So that you can definitely do it as a home exercise, and please calculate and check. Whereas when you calculate the reactions as such, reactions, again I have told you, there are two methods. One is the first row, QA11 Q1 plus K12 Q2 plus K13 Q3 minus F1. This is directly, it will give you the, you can say, reaction R1. So therefore, if you look at this, this is 0, K13 is 0. So what is the remaining is only this one. K12 being minus 3.33 into 10 raised to 5 into Q2 being 0.15 0.0009 minus 0 because there is no force F1 here. So if you calculate this, this will come minus 49.997 into 10 raised to 3 Newton. This is going to be the reaction at the first support, that is first one. In the similar way, can you tell me how to find out the support reaction at this one? It is again going to be K31 Q1, K32 Q2 plus K33 Q3 minus F3. This is how you have to find out. Once again, you know Q1 is fixed already, so therefore this is 0. And as far as this figure is concerned, you will get that also. That's it. Hi, class में किधर चल? Class में है? हाँ. बुक में कौन? See, once you find out in the similar way, the reaction R3 can also be found out in the same way. Okay, we can find out that and write down the values. So here again, I will give you the value of R3. This comes out to be minus 10.00019 into 10 raised to 3. So please compare this again. As well, when you add reaction R1 and R3, they will definitely tally with the total load of 60 kilonewtons. So this is one method what I just wanted to tell you like this. Now, let us go back to the same problem with penalty approach. In the penalty approach, what we have to do? That is very, very important part is the penalty approach. Okay. Okay, let us keep everything same. This will be changing now like this. Okay. Now look at this. How is going to be our penalty approach? First, I told you K11, K12, K13, K21, K22, K23, K31, K32, K33. I will write first the normal FEM equation Q1, Q2, Q3 is equal to F1, F2 and F3. See, I will write this particular simple equation. Before we start applying the boundary condition, we want to first apply this and then we will check the other method. For example, now let me solve it by penalty approach. Penalty approach. See, the penalty approach, always it says that you have to replace the support by a spring of very high stiffness. And the method of selection of the stiffness of that has been given as maximum of Kij into 10 raised to 4 Newton per millimeter. This is the first parameter to be always selected that. So therefore, if you look at this, you let us say go to this particular table, highest Kij is what? This and this. That is together this among all the 9 elements, the highest Kij is 6.66. So therefore, in the present problem, it is 6.66 into 10 raised to 5 into 10 raised to 4. So that is together it is 6.66 into 10 raised to 9 Newton per millimeter. But for by convenience, I will tell you the most important convenience why we require is this 10 raised to 5 being common here. I will convert this into 6.66 into 10 raised to 4 into 10 raised to 5 I will make it. Why I will make it? I will just show you this here. Now, once we found out the value of C and we are required to incorporate the boundary conditions, how to incorporate the boundary conditions? See, in the penalty approach, I have already told you, if your first node, if it is going to be specified with certain boundary condition, this large number C gets added to that. That is the one important equation. Then this will remain same. K12, K13 will remain same. K21, K22, K23 will also remain same. K31 will remain same, K32 will remain same. Only change is along the diagonal when I go, since at the third node, again you have the second boundary condition specified. So therefore, I need to add again this stiffness, large stiffness C at the third row also. So along the diagonal, you have to go on adding the boundary conditions there. So according to us, first plus C has been added here, plus C has been added here. Then the nodal displacement vector will remain same. Q1, Q2, Q3, they will remain same. Whereas in the global load vector, what is the change you are expecting is F1 is getting added with CA1, whereas F2 will remain same, whereas F3, where again boundary condition is there, the third boundary condition is going to be inserted there. So this is going to be the modified global equation before solving this. If we solve, see the only difference here is in the previous elimination approach, after elimination, the global size of the stiffness matrix, which was earlier n by n, has been changed to maybe, if you are removing only one row and one column, then it will be n minus 1 by n minus 1. If you are removing two rows and two columns, it is n minus 2 by n minus 2. The size of the global stiffness matrix, everything will reduce there in the elimination approach. Whereas in the penalty approach, is not going to take place. The original size of the stiffness matrix and everything will remain same. Only thing is, after solving, you will get the simultaneously, after solving all the three equations, you will get Q1, Q2, Q3. All the three will come. But only the difference here and there is, there we used to take Q1 as 0 itself. Whereas here, you will not get them as directly 0. You will get such a small value, as I told you, like 0.7568 into 10 raised to minus 6, minus 5, minus 8. Like that, that number is almost to be neglected as considered as 0. But it will not definitely it will not be coming as 0. We have that importance of that. So therefore, according to this, now I am changing this. Now the significance of this step, now we will come to know. See here, why you will come to know. For example, if I want K11 plus C, if I want to write this, what is my K11? You tell me here in this equation. It is 3.33 into 10 raised to 5. And this is added with C, which is C is 6.64 into 10 raised to 4 into 10 raised to 5. So this, if I take it as 3.33 plus 6,000, if I take this as this one, 66400, you will get into 10 raised to 5, you will get. So when you add this together, what you will get is 66603.33. You will get this into 10 raised to 5. So this number will appear in the first way, because 10 raised to 5 being common, I am going to take it out here outside. So this is the reason why I purposely wanted to make that. That's now I think you can see there 10 raised to 5. I will show it here. This number will now come here 660 or 66603.33. This 10 raised to 5 has been already taken care of outside. The remaining thing will remain same only, minus 3.33, and this will remain 0. This is minus 3.33, 6.66, minus 3.33, 0, minus 3.33, but once again here you will get 660, because the last number is also the same. First and last number for this particular problem, since it is uniform cross section, this number will not change. So therefore, this is also going to be the same thing which will come here. Now, this is being multiplied by Q1, Q2 and Q3. Okay, and next here, when I want to find out the global load vector, it is 0 plus, because F1 is 0 here and A1 is also 0, but still I wanted to show you that our 6.64 into 10 raised to 9, this is being the C value, and A1 is 0, so there is no consideration of that. That will automatically get cancelled there. Then as far as the second F2 is concerned, the load is how much? 60 kilonewton. So 60 into 10 raised to 3 will come as usual. This is the F2. F2 will not be modified. Whereas when it comes to F3, this is going to be 0 plus 6.64 into 10 raised to 9. That is C. And of course, your A3 is not 0. It is going to be 0.12. See here it is CA3. This is nothing but this is CA3. This is CA1. And A1 is 0. As you know that node 1 is fixed and therefore it is considered as 0. Whereas in the case of node 3, this additional term getting added to that. So now we are solving all the three equations simultaneously with the help of your calculator or solving. So on solving, what we will get is Q1 will come 7.504354512 into 10 raised to minus 6. As I told you, it will not come directly 0. It will come some very small number, that is 10 raised to minus 6. Whereas if you take the Q2, it is coming 0.1500945 mm. And if you go to Q3 again, here it will not exactly come 0.12 only, you will get 1504. Yeah, this is what you are going to get. So these are the three nodal displacements what you are going to get from this equation. Why this is not coming 0? Because for finding the reaction, what we have to do, for example, I want to find out the reaction at node 1 and node 3. How exactly this is to be handled? Okay, see, for example, I will take the reaction R1. This reaction at R1 is directly given by C into bracket Q1 minus A1. Directly it will be given there. So therefore, if I take this, it will be minus 6 point, our C value 6.64 into 10 raised to 9. 6.66 into 10 raised to 9. And what else? Minus 0, because it is 0. So therefore, I will get this reaction. Yeah, of course, this is 0. This is to be, of course, multiplied by Q1. Q1 you got it as 7.50453 0.43545 into 10 raised to minus 6. And since A1 is 0, I will consider this. So when you calculate this, this R1 comes out to be minus 499979. This is what you will get. This is very much closer to the answer what you had got it from the elimination approach. In the similar way, you calculate the reaction here, which is going to be C into bracket Q3 minus A3 to get the reaction at the support 3 at node 3. We have to calculate this, which is nothing but minus 6.66 into 10 raised to 9. Q3 being point, this is, look here, if you, by chance, if you did it as just directly neglecting all the terms here, then you will get the reaction as 0. This need to be considered because A3 is 0.12. Whereas the nodal displacement Q3, what you calculate, it is slightly more than that. So when you really take these two, you will get 116.64 Newton. So this and this, when you add it together, once again they should come equal to the, what you can say, the total load which is going to be applied there. So I think definitely you can compare the displacements and the reactions, what has been obtained from elimination approach as well as from the penalty approach. We find very close resemblance. See, there is a provision that for taking the value of C, we take the largest Kij. It is multiplied by 10 raised to 4. If you want to improve the answers, 10 raised to 5 is also in some of the books it has been referred that instead of 10 raised to 4, you can even take 10 raised to 5 and you can make the calculation. But only one important point you remember, since there is an approximation between the Q1 and the A1 and all that, the reactions are not very accurate. We may get a small change, but that means when we add R1 plus R3, it may not be exactly equal to the total load. It may be slightly more or less equal to the total load, because that small, you can say, computational error will come when you are solving by penalty approach. So therefore, it is very simple, especially the difference between elimination approach and the penalty approach is, suppose your equation, like your structure is very large, and if the global stiffness matrix is of, let us say, 5 by 5, it is a global stiffness matrix is 5 by 5. Whereas in the elimination approach, for example, there are 3 supports. So therefore, 3 rows, 3 columns will go, and finally the equation to be solved will be a 2 by 2 equation. But in the case of penalty approach, the original size 5 by 5 will remain same. That means you need to use a special technique to solve a 5 by 5 set of linear equations, and then you have to get the 5 displacements. This cannot be done by your ordinary calculator and all that. Then you have to go for Gauss elimination method or Cholesky method or any other method to solve method for solving simultaneous equations. So that you have to use and you have to solve it. But as far as the problems which are concerned coming across to you people, generally we solve 3 by 3 is the maximum. So therefore, that can be easily solved by your calculator and can directly get the solutions. But for higher, you can say, degrees of freedom, you need to follow the different methods. Now, one more last problem I wanted to solve in this particular thing. Today, I will give you the introduction about that particular problem, and then later on, the next class, I will be covering one more problem related to considering the self weight of the structure also. We consider that. Okay, one simple problem I just wanted to show you before I close for today's lecture. I will give you some introductory part of this, then we will solve the detailed thing. See, suppose I will consider one a triangular plate. This is the triangular plate, and this is what is called as this one. And it has got, let us say I will consider one midpoint here. This is being, let us say, L1, and this is being again L1 only. It is a midpoint I am considering here. Let us say that the width of this is the width of this side. This is called as the width, and this is again the width of this. This is the W2. And if you look at the side view, it is going to be a thin plate. The side view of this plate is going to be a thin plate of, let us say, thickness T. T is the thickness of this plate. If you want to look at this figure in an isometric way, see, this is going to be the, what you can say, the plate. That is, this is having like this. This is the area A1. If I want to say, it is definitely W1 into T, this area. And here again we will get this one. Like if you take this one like this area is called as A2. This is W2 into T, like this. You can find out. But in the inert element equation, we are already knowing that this type of taper elements are not being used. For maintaining that, we need to convert this figure into an equivalent elements of uniform cross section or uniform length and uniform size. So to convert that to uniform size, how to do that? See, for example, I will first find out the area at this point, that is the midpoint. This is, let us call it as, let us say, W middle, you can say, that is the W middle. So therefore, W middle is always obtained by average of these two widths, W1 plus W2 upon 2. So naturally, this is going to be Wm. See, let me divide this figure into two parts, 1 and 2. So now presently what I get is now, first part is now like this, which is being W1 and this is Wm. And the second part is going to be Wm and W2. This is what I am going to get this. So now we want to convert by using what is called as midpoint rule here. I want to add and subtract some material here, and here also I want to add and subtract, so that this will look like a figure which is a pure rectangle here now. I want to show like this. That is, whatever is there extra here, and here, I want to add it here and make it a rectangle here. Similarly, if I take the midpoint rule here also, again I will take this, convert this, and again I will convert this into this, and this extra material, whatever is there, I will transfer it here, and I will get another smaller element, I will get it here now. Okay, this is now going to be the new element, whatever I got. So therefore, to find out this new width, like let us say W1 dash, if I want, it will be the average of Wn upon Wm. This is going to be the uniform width of this first element. Whereas the uniform width of the second element, if I want W2 dash, it is Wm plus W2 upon 2. This will give me the next, what you can say, area. So because of this, the structure now it is getting modified to a bigger element attached with a second element. If you look at this isometric view, it is now going to be like this now. This type of element you are going to get, and therefore these new areas, let us say if I take this as our A1 area, it will be W1 dash into T, and if I want this area A2, it will be equal to W2 dash into T. So this is the modification. First we need to convert from taper sloped area to the uniform area. So then it will be simple for us to consider it as two elements, like this is fixed here now. Here let us say you may give one point load also, and here all this is given, like this is again. Please remember, this will remain as L1 only. These remain as L1, both will remain L1. Only the change is areas have been changed here now. So this is the form. Next, another very important point is the body force. See, the body force or the self weight, body force is always expressed per unit volume. It is always, please remember. This is always called as F. Generally it is given as rho g. F is body force per unit volume is given as rho g, where rho is the mass density. It is the mass density kg per meter cube, and g is the you can say constant of acceleration 9.81, which is equal to 9.81 meter per second square. So when you multiply both of them, you will get the mass per unit volume. This is what you are going to get this. To get the, or sometimes in some books they will give you, instead of this they will give you weight density. They will call rho as weight density. In that case, weight density is directly, it is, the unit will be Newton per millimeter cube or meter cube. Directly you will get that in. So to get the body force vector, body force, total body force if you want, it is rho into A into L. This is going to be the Newton. That is, rho is the new weight density into area of cross section into the length. That will always come there. So obviously this has to be considered as F is equal to, that is body force vector is rho AL upon 2. It is 1 and 1 for each element. It is going to be distributed. This is the load distributed at node 1, and this is the body force acting at node 2. So by considering this, we need to solve the equations related to that, and then we will find out the effect of that. So naturally, when we want to find out this, for this particular problem, since area and L1 are different, so I can rewrite this as rho A1 L1 upon 2, 1 and 2, 1 and 1. Whereas for the second element, what is there in the bottom, if I want, it is going to be rho AL or rho A2 L1 upon 2 here, because L1 remaining same. This will be 2 and 3. This is the nodal connectivity with that. So now, using these all the three, if I want to convert the, you can say, global load vector, what are those? See, at the first node, only this is there. That is rho A1 L1 by 2 is there. Similarly, at second node also, I have this. But in addition, there is a contribution of this. This is also going to be adding there. So therefore, I need to write rho A2 L1 upon 2 also I have to add. Here again rho A2 L1 upon 2 is going to be there. But interestingly, if I add, suppose for example, this figure you see there, at a node 2, if I add one more, you can say point load also, so that point load gets added here. This will be what is called as the global load vector F, which will take care of the body forces which are acting on the element, as well as the point load which is acting at the node 2. So this will be completely what is called as, let's say, the global load vector. And the remaining problem can be solved in the simple manner. That is, you can directly solve it as K1 plus K2 because it's a two element member. Find out separately element stiffness matrix for first element number 1 and then element number 2, and then find out the global stiffness matrix. Then there are 3 displacements, and use this global load vector and then solve for it. The very interesting point you have to note down in this problem is while finding the reactions. Because in elimination approach we have seen all the multiplication minus F1 when we write, we generally say, oh, there is no force acting at the node 1. But in this particular type of problem, node 1 also carries this much amount of force. This amount of force is already acting due to self weight. This much amount of force is already acting at the node 1. So therefore, I cannot simply say minus 0. Now all this like K11 Q1 plus K12 Q2 plus K13 Q3 bracket complete minus F1 is nothing but FA1 L1 upon 2. That you have to consider. That will give me the correct reaction. So we'll take up one interesting problem in the next class, and then I will discuss about the effect of temperature, how temperature difference also causes stresses in the members, and then how to find out the resultant stress due to both the temperature as well as the given applied mechanical loads. So that analysis we will take up in the next class. We will discuss about that.